Hello everyone. In this video, we will be talking about covariant and contravariant vectors. So let's first talk about contravariant vectors. Here we have two sets of coordinate systems. One of them is x and y, and the other one is x primed and y. Now we have a vector here, v, where v is equals to 4i hat plus 6j hat. Now if we transform this coordinate system using a linear transformation matrix and shift it to this new coordinate system, what happens to the vector v? Well, it turns out that v becomes equal to now our transformation only took x to x primed. It didn't change the y coordinate, and our I hat basis vector was changed to I primed, where I primed is equals to 2i hat. So when we do the transformation, it turns out that the x component of the vector v is halved, but our transformation originally doubled the basis vector. So here we are seeing that our transformation is to get our x coordinate double, but the x coordinate of the vector gets halved. So there is a reverse action going on. So we can say that this sort of vector are called contravariant vector. Contra because it's doing the opposite of our transformation matrix. Contravariant vectors. Now let's talk about covariant vectors. As you can see, I have drawn out a function k, where k is a function of x and y, and I have represented how k changes with x. Now here we can see that before the transformation there is a change in k for some change in x, and after the transformation that same change occurs over half the distance. Why is that? Because we've done the same transformation here, but as you can see, if we double our basis vector, then the x coordinate of our vector gets halved, meaning any displacement in the x direction will also become halved, which is why you can see that 0.05 is being halved here, 0.025. Right, so let's look at the gradient vector. Now if you are unfamiliar with gradient vector, I would suggest you look into vector calculus first, and then look at these videos. Right, so what's the gradient vector? Well, the gradient vector acted upon k is just change in k over change in x. Since k is a function of x and y, we will have in the I hat direction change in k by change in x, and change in k by change in y in the j hat direction. That's for this part right here, this graph right here. And what will be the gradient vector for this part of the graph right here? It would be change in k over change in x primed, since we've changed our x coordinate, I primed, oops, this would be I primed, plus we haven't changed our y coordinate, so it would stay the same, a hat, right? So this would be for this part of the graph right here. Now, why is the gradient vector a covariant vector? Well, let's see, for this part of the graph, we won't compute del k by del y in the j hat direction because they are the same in both of these expressions, but we'll take a look at del k by del x in the I hat direction. So this is just the change in k over the change in x 5 in the I hat direction, right? And the same change in k over change in x prime in the I prime direction. We'll compute this. So for this same change will occur for half the distance, so it would be 0.025 in the I prime direction. Now notice that 0.025 is half of 0.05, right? So 0.05 I primed. So this is basically 2 into change in k over 0.05 in the I prime direction. Now compare these two values. We can see that the component of the gradient vector, this component right here, as we have changed our x coordinate into x prime by doubling our basis vector, we can see that our component of the gradient vector, this I hat component of the gradient vector, is being doubled. See right here that del k by 0.05, and here is 2 times del k by 0.05. So as we have doubled our basis vector, the component of the gradient vector is also doubled. So these sort of vectors are what we are calling covariant vectors. Covariant vectors. Why covariant? Because it is doing the same thing as the transformation. Okay, now let's move on to the projection part. Okay, so here I have drawn out, in general relativity you will always find space is curved, meaning the coordinate systems will not be orthogonal. In Cartesian coordinates, x, y and z, they are orthogonal, right? X, y and z, they are perpendicular to each other. But in general relativity, x, y, z won't be perpendicular to each other. They may be curved, they may be oblique. So in those cases we have to look at non-orthogonal coordinates, right? So I have drawn a coordinate system consisting of two coordinates where the basis vectors are e1 hat and e2 hat, and there is a vector a in this coordinate system. Now if we project a parallelly to e2, then we get a component, right? That component is denoted as a superscript 1. Now why did I write a superscript 1? Because remember that when we parallelly project this a vector on the base right here, we would get the contravariant component of a, right? Why contravariant? Because look here, when we had, say, we doubled our basis vector from I hat to I primed, right? So here the components where the contravariant vectors, right? Components of this vector were the contravariant vectors. Why? Because as we doubled our basis vector, these components was halved. So in tensor calculus, contravariant components are denoted with superscript and covariant components are denoted with subscripts. So the coordinates of this vector A, coordinates of this vector V via the contravariant vectors of this vector. So likewise, the parallel projection of A would be the contravariant component of A, and we did the same thing, that same parallel projection in this direction. We got A2. So this vector, if this was some sort of displacement or any normal vector, this could be written as A is equals to vector A is equals to A1 E1 hat plus A superscript 2 E2 hat. So this is for any normal vector, right? But what if A was a gradient vector? For gradient vector, we would have to project them perpendicularly. Why? Because in calculus, we have always done gradient as, say, let's say we have df by dx, right? So this would be change in f in the vertical direction, change in f, like say we have a coordinate system here. This represents f, this represents x. Now say this is a function, so the change in f df should be this vertical section right here, right? Should be this vertical section, and change in x should be this part right here. So we cannot say that the parallel projection could be gradient. Why? Because parallel projection, in parallel projection, the gradient turns out to be, say, this change right here, this change, say I call it del f, and this change right here, say I call it del x. The gradient, a gradient cannot be, sorry, say I write it as m. Gradient cannot be del f by del x. It cannot be this case, because in calculus it was always perpendicular. Rise over run, it was always perpendicular. So if we have to denote a vector A that is a vector, a gradient vector, it would definitely be this vertical component divided by this horizontal component, right? So this A1 would be our del A by del x, right? So that would be our A1 covariant vector. Why covariant? Because gradient vectors are always covariant vectors, right? So if A was a gradient vector, then it could be written as A is equals to A1's, where 1 is the subscript, E1 hat A2 E2 hat. Now in tensor calculus, we have to maintain our index. So if there is a lower index, if the right hand side contains no index, say A has no index here, so the left hand side has no index, the right hand side should also have no index. How can we make that possible? See, there is A1 and E1 on the top for this part right here. So these ones and ones, they cancel out. Likewise, A2, E2, these 2 and 2, they cancel out. Overall, leaving us with 0 index on the right hand side. So tensor equations always maintain this index numbers on both sides. Right. In the next video, we will be talking about how tensors transform. So see you on the next video.